So she got her PhD at Cornell, then after postdocs at Yale and in Berlin, she got her professorship at Texas A&M, and now she's a professor at the University of Washington. And she will tell us interesting things about graphical designs. So go ahead.
Thank you. So thank you again for having me. And I'm sorry that I can't be there. It's a little frustrating. I'm actually in Bangalore, but in a relative's house because my daughter has COVID. So anyway, here we go. I hope you enjoy the talk, even if it's by Zoom. Okay, so I'm going to talk about something called graphical designs. And this is a relatively recently introduced concept. It was introduced by an analyst, and I will explain where it comes from and what motivated it. Everything I say today, oops, I don't seem to be able to advance my slides. Let me see. There we go. Okay, everything I say today is joint work with Catherine Babecki, who is my PhD student at the University of Washington. Okay, so let me start by talking about what motivates this concept of graphical designs. It's motivated by the classical idea of a spherical design that many of you may know, and for related work, Marina Wiasowska just won the Fields Medal. It's a beautiful object that is a quadrature rule on a sphere. Okay, so a spherical quadrature rule on the unit D sphere is just a collection of finitely many points. Let's call it x1 through xn. And they come with weights. So let's call the weights AI. These are real numbers. And what they have to do is that for sufficiently smooth functions f, the global average of the function on the sphere, which is what you see here on the left-hand side, has to be roughly equal to the weighted average of the function values at these points, x1 through xn. So the weights are these AIs. They have to be prescribed along with the points x1 through xn. And if you're able to do this, then we call x1 through xn along with the weights a spherical quadrature rule. Okay, so this is sort of the bread and butter of numerical integration. If you want to integrate a function on a domain, such as the sphere, let's say, you want to, at least on the computer, find some finitely many points at which you can calculate the function values and then just take this weighted average, and that'll do the job of actually integrating over the domain. Okay, so this is a spherical quadrature rule. And on the sphere, the right functions to integrate are the spherical harmonics. Okay, so spherical harmonics are simply polynomials. So these are polynomials restricted to the sphere, but they're also harmonic polynomials. So what spherical harmonics, and they're organized by degree. So in general on a sphere, we say that you have a spherical T design if the collection of points x1 through xn will integrate all polynomials of degree at most t. Okay, so we only care about polynomials restricted to the sphere that are harmonic. Harmonic means that it has to be annihilated by the Laplace operator on the sphere. Okay, so on the left here, you see a spherical 5 design. So this is a 5 design on the 2 sphere. So these are 12 points. They correspond to the vertices of a regular icosahedron that's inscribed inside the sphere. And here the weights are uniform because of the very high symmetry of the sphere. So if you integrate a function on the whole sphere, basically a polynomial of degree up to 5 on the whole sphere, integrating that is exactly the same as calculating the function values at these 12 points and then adding them up with weight 1. Okay. So this is the idea of a spherical design. So with more and more symmetry in the domain, you get more and more symmetric points that will do the job. Okay, so the idea now is to pass to the domain of graphs. So these designs are what were classically defined over continuous domains. So now I'd like to tell you how we could do something similar on the domain of graphs. Okay. So in this talk, we'll just focus on a very simple type of undirected graph. So G is a graph with vertex at V, edge at E. It's finite, it's simple, meaning there are no loops and no parallel edges, and it's a connected graph. Okay, so let's assume all that for right now. And then first of all, a function on a graph is simply a real valued function on the vertices. So you're just putting numbers on the vertices. And we're going to say that a subset W of the vertex set V, along with some weights, which let's call them AW, these are real numbers. We say that this averages the function F if you get exactly what you saw in the previous slide. So on the right here is the global average of the function on the whole graph. And on the left, you should be able to capture that average by making the weighted average of the function at these points that are inside W, okay? So this is what it means for a subset of the vertices W along with weights to average a function. So this is a very, very basic and important concept in this talk. So let me actually do an example. So here is the Peterson graph, and on the right, you see a function. These are just numerical values on the vertices. And if you look quickly at this function, you will see that the global average is 0. So 1, -1, 1, -1, 2, -2, and -1, 1. So the global average is 0. And these values have been distributed on the vertices of the graph. So everything is ordered. You can't quite see the ordering on the vertices, but this is how it should look. And now what we would like to find is a subset of the vertices whose average with weights will be exactly the same as the global average. So let's see two types of examples. So on the left, you see these red vertices. These will average that function, meaning that if you make the weighted average of the function values on the red vertices with just the 1, 1, 1, 1, 1, 1 weight, then that'll also give you 0. So again, you can check, here's 2, -2, -1, and 1. So the average on the red vertices with the uniform weights, 1, 1, 1, 1, 1, is the same as the global average. Okay, so this is what we will call later a combinatorial design. So these are situations where the weights are just 0 or 1. And on the other side, you see a more interesting type of design. So these vertices, the colored ones, the pinks and the red, they also will average the same function, but now the weights are not uniform. And the pink ones correspond to the weights 1/3, 1/3, 1/3, and the red one corresponds to the weight 1. So again, if you make the weighted average, you'll see this is a 1/3 plus a 1/3 plus a 1/3, that's a 1. And then that's going to get multiplied by added to -1, which will give you 0. Okay, so these are two types of subsets with weights that will average the function. And the second one is more versatile because we are not requiring it to be 0, 1, but it's non-negative. So non-negative will play a very important part in the talk as well. And the different colors you see here, the different shades of red are going to indicate different magnitudes for the weights. Okay, so you'll see this type of picture again and again. Okay, so that's the notion of averaging a function. So the next question is, which function should we average, right? On the sphere, it's the spherical harmonics. That's pretty clear. And it's because the space of all functions on the sphere can be written as a combination of spherical harmonics. So you want to go degree by degree. And if your function is relatively smooth, then you need very low degree spherical harmonics. And therefore we have to, so that's definitely the natural set of functions to average on the sphere. But on the graph, what should be the right function? So what are the classes of functions we want to average? So let's think about that for a moment. So now for the rest of the talk, I'm going to make it even simpler. I'm going to assume that the graph is regular. Okay, this is not required, but it actually makes the technicalities a little bit easier. So let's go with the regular graph. And the correct functions to integrate or average rather are the eigenvectors of some sort of Laplacian of the graph. Okay, so because I have a regular graph, it turns out that we can just work with this very simple matrix, which is the adjacency matrix of the graph, times D inverse, which is the diagonal matrix that consists of the degrees of vertices on the diagonal. So let me pause for a moment. So A is a square matrix of size cardinality V by cardinality V. It consists of 0, 1 entries. It's the adjacency matrix of the graph. And it's defined by saying that in the ij entry, you will put a 1 if and only if ij is an edge in the graph. So this is a symmetric 0, 1 matrix, square matrix. And D, because I'm choosing my graph to be regular, this is supposed to be the diagonal matrix with the degrees of vertices on the diagonal, but all the degrees are the same because our graph is regular. So this is just a scaling of the identity. So A times D inverse is just basically a scaling of the A matrix, the adjacency matrix. Okay, so this is a choice we can make. As you'll see, it has some advantages. You could also work with the regular graph Laplacian or the normalized Laplacian. It turns out they're all equivalent for a regular graph because of the eigenspaces are all the same roughly, and the eigenvalues just shift around. So we're going to work with this one. So here's an example. So here on the left, you see the icosahedral graph. And the icosahedral graph has 12 vertices. So AD inverse is a 12 by 12 matrix. A is a 0, 1 matrix, and the 5s that you see in the denominator come from the D inverse because every vertex has degree 5. Okay, so this is a symmetric real matrix. Therefore, it has all real eigenvalues. And because of the way we have defined it, this AD inverse, it's actually a doubly stochastic matrix. So all the rows and columns sum to 1, which means that the spectrum of this matrix lies between 1 and -1. So this is the reason why we bother with the D inverse. Otherwise, you could also just use A, okay, for a regular graph. So let's do this. So the spectrum lies between -1 and 1. All the eigenvalues are real. The biggest one is 1. The dominant eigenvalue is 1. So this is the matrix that we want. This is going to play the role of the Laplace operator on the sphere. And what we want to average are the eigenvectors of this AD inverse, okay? So here again is the same example. And now you see the eigenvectors of this matrix, which is, this is an eigenbasis, and it's been written in terms of the different eigenspaces of this matrix. So this matrix has 4 distinct eigenvalues that you see on the left here. The first eigenvalue is 1, and an eigenvector that spans that eigenspace is just the trivial 1, 1, 1, 1, 1 vector. We'll call this the trivial eigenspace, the top one, and the vectors, the trivial eigenvector. Then after that, the eigenspaces have a dimension, positive dimension, I mean, bigger than 1 dimension, or in other words, the eigenvalues have multiplicity. And here again, you see in the rows of this matrix, the different eigenvectors. They're all orthogonal because of the fact that I can do that because I have a symmetric matrix, they're orthogonal, but I'm not going to orthonormalize them because we want to keep vectors like 1, 1, 1, 1, 1 around. I don't want to orthonormalize it, okay? But they're orthogonal. So this 12 by 12 matrix again that you see here is an eigenbasis of R to the 12 coming from this AD inverse. Okay, so that's basically the functions we're going to try to average. We're going to try to average the different eigenvectors and I'll explain how, in what order we want to do them. So one strange thing you might notice about the way this matrix is written is that the eigenvalues are not written in increasing order. So typically eigenvalues are written in increasing order, but here they're actually written in decreasing order of absolute value. So the top one is 1, then the next 2 have the same absolute value, 0.44, and then the next one has a smaller absolute value, which is 0.2. Okay, so this is a very special ordering. This is called frequency ordering, and again has physical interpretations. It comes from the analysis side. And these eigenvalues, so basically what these eigenvalues are doing is they are sort of ordering the eigenvectors from the outside in. So the biggest one is 1, the next one is close to -1, then the next one is close to 1, and then the next one is inside. So it goes from the outside into the inside. Okay, this is called frequency ordering. And as we'll see shortly, it measures smoothness, a notion of smoothness of functions on the graph. Okay, so these are the functions we're going to try to average. Okay, so let me say one more thing about these functions. So the first eigenvector, which is this top one, is 1, as we just saw. It's the vector of all 1s. And notice one other thing, that if we take any other row of this matrix, let's call it Fj, this is an eigenvector from this collection, then because of orthogonality, 1 transpose Fj is 0. 1 was the top eigenvector, so all other eigenvectors are orthogonal to it. But if you look at that one more time, you'll see that that means that the average of all these other eigenvectors other than the trivial one is 0. Okay, so this is actually very convenient. And this is also follows from the fact that we have a regular graph. And so this is something that will play also an important role in what's coming. So all eigenvectors we wish to average, except for the top one, have average value 0. And that makes it really, really nice and convenient to find these, find what I'm going to explain our designs. Okay, so that's another feature. Okay, so before I tell you what a design is, let me actually try to sell you this notion of frequency ordering, because I think it's very cool, and it sort of measures a type of smoothness on the graph. Okay, so here's a graph. This is the graph of the contiguous United States. There's a vertex for every state, and there's an edge between two vertices if the states share a border. Okay, and this is not a regular graph, but it's an irregular graph, but it doesn't matter. The concept can be explained just as well. So here are the eigenvectors. It has, some large number of eigenvectors, and let's say we have ordered it according to decreasing absolute value. And you see here in this left side, the first eigenvector in this frequency order. And if you notice the color coding corresponds to the magnitude of the entries in the eigenvector. And you see that it's fairly smooth. It actually varies rather smoothly across the United States. Here is the second eigenvector by frequency. It's slightly less smooth, but it's still pretty smooth. And if we keep going, here is the 11th eigenvector, and you see that it's pretty jumpy. Okay, it's not that smooth. And this is exactly what frequency order will do for you. It is measuring the eigenvectors according to their smoothness, or it's a little bit more complex than that, but roughly speaking, it's ordering the eigenvectors by smoothness. Okay, and this is of big practical relevance, because if you think of some sort of continuous function that varies across your graph, like say precipitation, then it's more or less going to be made up of these low frequency eigenvectors. Just like in Fourier analysis, we expect smooth functions to be made up of low frequency modes of the Fourier series. So similarly here, we expect most functions to be made up of low frequency eigenvectors if they're relatively smooth. And so we're going to try to average eigenvectors in this frequency order. Okay, so this is basically the idea of frequency order. So that gets me to the definition of a graphical design. So let me explain what that is. Okay, so we have this graph G, and we've ordered the eigenspaces. Let's assume there are m distinct eigenspaces. They may have dimension more than 1. So I'm not assuming that the number of vertices is the same as the number of eigenspaces. So m is the number of eigenspaces. And we order it some way. It doesn't have to be frequency order. In many of my examples, it will be frequency order, but just fix an order. Now, after you fix an order, then here's the definition. So a K graphical design in G is a subset W of the vertex set V, along with weights, which are real numbers, that average the first K eigenspaces, okay? So in other words, what we want to do is to average every function in these first K eigenspaces, which is the same as averaging a basis for each of these eigenspaces from lambda1 up to lambda K. So this definition was made by Stefan Steineberger, who's one of my colleagues at the University of Washington. And as I said, he was motivated by the notion of spherical designs. So this is what a K graphical design is. So it's a collection of vertices with weights that's going to average the first K eigen spaces of the graph. Now, depending on the type of weight you ask for, you can get different types of designs. So if you ask for no restriction on the weights, they're just real numbers, then we will get what I will call a weighted design or an arbitrarily weighted design. If you're interested, if you require the weights to be non-negative, then we'll call this a positively weighted design. And if you are very, very restrictive and ask that the weights be 0, 1, then we call this a combinatorial design. So as you see, they're going to get progressively harder and harder to find. And you'll see different types of examples. So positive, now 0, 1 weights, of course, very, very nice. And they happen in very symmetric examples. You will find designs, small designs with 0, 1 weights, but they are not always possible. It's not always, they don't always exist. Whereas you will see later that positively weighted designs will exist for every value of k. And positive weights are definitely more attractive than arbitrary weights in this business. Just like in numerical integration, people like quadrature rules with positive weights because those are just a lot more numerically stable than just arbitrary weights. So people don't really like negative weights. And you'll see in this story too, the positive weights are have a very, very nice theory that go with them. Okay, so this is what a graphical design is. Right. So let's do some examples just so the definition is clear. So let me come back to this icosahedral graph. It had 4 eigenspaces, and let's say we want to average the first 3. So I have ordered them in some way. This is not frequency order. So lambda1 always has to be first, the trivial eigenspace, but after that you can put it in whatever order. So this is the order that I've put it in. And on the left here, you see an arbitrarily weighted 3 design. So that means this is a design. These colored vertices form a design that can integrate lambda1, lambda4, and lambda3, okay? And this happens to be arbitrarily weighted and contains 7 vertices. The blue vertex here has a negative weight, and the pink and the red vertices have a positive weight. So it has 7 vertices, and it can average everything except the last eigenspace. Here's one that is also a 3 design, meaning that it can average the first 3 eigenspaces, but now it's positively weighted. So it has more vertices in it. It has 9 vertices, as you expect, because we are requiring more of the weights. And then here on the extreme right is a combinatorial design, but it is not a 3 design. It's only a 2 design. There is no 3 design that is combinatorial. So this is what I meant by saying that if you insist on combinatorial designs, you may be fairly restrictive and not be able to average as many eigenspaces as you can with positive weights or with arbitrary weights. Okay, so this of course is so this is an example, right? So let me make one more definition before I tell you the results. So now that we've defined what a graphical design is, the thing in practice we want to do is to find designs, small designs, that can average as many eigenspaces as possible. Okay, so if we have m eigenspaces, then we could say, okay, is there a set that can average everything, every possible, a proper set of vertices that can average everything? Unfortunately, no. Okay, so we cannot have any proper subset that can average all the eigenspaces. So the next best thing we can ask for is, can we find designs that can average all but the last eigenspace in our ordering? And such designs, we will call them extremal designs. So these are designs that are m-1 designs, meaning they can average lambda1 through lambda m-1. And this notion was introduced by Konstantin Golubev in a paper in 2020. And he was interested in some theoretical computer science connections to designs. And he introduced this notion. Okay, so coming back to our example, extremal design in this ordering means that we want to average lambda1, lambda4, and lambda3. So everything except the last one. And the first 2 designs here are extremal. They're extremal 3 designs. But this design on the right, which is only a 2 design, is definitely not extremal because it's not able to average everything except the last eigenspace. Okay, so this brings us to the various questions we can ask about designs that we asked ourselves when we got started. So one question is, how do you compute K designs? Okay, so is there some sort of algorithm we can write down? How fast is it? How hard is it? How does one compute K designs? And secondly, even more ambitiously, how do you compute the smallest K designs? Because those are, of course, the best. We want very small K designs. So these 2 questions are definitely optimization questions. And we worked on this for a while. We had different types of algorithms and complexities. I mean, actually, yeah, not so much complexity, but we worked on these algorithms. But there was nothing quite satisfactory that was happening with these 2 questions. So then at some point, we realized that you can actually answer a much more complicated and interesting question, which is, you can ask yourself, is there a way to organize all K designs? Is there some sort of structure behind them? And it turns out that there is some very organized way of writing down all K designs if you fix a K and some graph G. And that's basically what I would like to tell you about. Okay, so maybe I can stop for a moment just to make sure that the definition is clear before I tell you the main theorem. So I cannot see you, so please just ask and hopefully someone can tell me.
Yeah, I want to ask, what is the meaning of averaging the eigenspaces?
Oh, averaging
I-
eigenspaces means you want to average every vector that lives in those eigenspaces.
as
So
a basis
averaging
element?
sorry?
As a basis element?
Yeah, so a basis is enough. So if you can average a basis, you can average everything. So it's enough to average a basis. That's why we only work with the bases for each eigenspace. Is that clear?
Yeah, one more thing, why there is no subset to average all the eigenspaces? Is there any particular reason?
Yeah, it's just you will if you ask for a proper subset and write down, it's a very easy contradiction. I can explain it later. You'll quickly run into a contradiction if you take a proper subset. Of course, if you take the whole vertex set, it will average every eigenspace, but that's not very interesting.
Okay, thank you.
Are we
Go ahead,
good?
Rekha.
Okay, great. Thank you. Okay, so let's talk about what we can do with this. So again, let me remind you what we are asking is what we want is some subset W along with weights AW, such that when you do sum of AW, FW over all the little W's and the big W, you get 0. And 0 is because the global average of all these eigenvectors is 0, except for the first one. Okay. So we want to do this for all F's that live in lambda 2 to lambda K. And the reason is because we avoid lambda 1 because any subset can average lambda 1. That's not very interesting. So we don't need to worry about the first eigenspace. So I'm asking to average everything in lambda 2 to lambda K. And that exactly means this equation being true, that the sum of AW, FW must be 0. Okay, so we want to find W and AW. That's the question. Okay, so here's the main theorem. And let me first tell you what the theorem is, and then we'll look at some examples. So the theorem says that the set of minimal positively weighted K designs. So minimal means that if you remove some element from the design, it's no longer a K design. So minimal positively weighted K designs are in bijection with the facets of a polytope. Okay, so the polytope is indexed by K bar when you're looking for K designs. So the K is the index on the left, K bar, which is the complementary set, is the index on the right. And I will explain what all this means. These polytopes are given in terms of vertices. So they are given as the convex hull of some vectors. And the bijection is sort of a complementary bijection. So if W is a K design, then V minus W indexes the facet. Okay, so the smaller the design, the more the number of vertices you will see on the facet. So this is the bijection. It's sort of an inverse bijection. And that is basically the main theorem. And for the experts, I will just say a word that this is basically a consequence of Gale duality, and I will explain that later in the talk as well. Okay. So pictorially, or just as a cartoon, this is what the theorem is saying. So for example, if you take the octahedral graph, so here's the octahedral graph, and you order its eigenspaces in a particular way, then there is some polytope. This blue polytope happens to be a triangle, and the facets correspond to the minimal positively weighted K designs for this particular value of K. It doesn't matter. I will show you more precise examples. So the facets correspond to the minimal designs, and the other faces, the vertices, they also correspond to positively weighted designs, K designs, but not minimal ones. So the theorem is actually about all faces of the polytope corresponding to positively weighted K designs, but the minimal ones are on the facets, and as the faces get smaller and smaller in dimension, you will get less and less minimal K designs. So this is just a cartoon just to illustrate the theorem. So this is the main theorem. And for the most part in this talk, I just want to try to explain this theorem. And if I have time at the end, I will show you some families of examples, but maybe I'll just focus right now on explaining the theorem. Okay, so this is the theorem. And I'm going to proceed by actually starting by first telling you a recipe for constructing this polytope. So I will not explain at the beginning why it works, but let's actually just write down the recipe and see a bunch of examples and then get to why it works. So here's the recipe for constructing the polytope. So what we do is we first collect in this bold K, it's a set, we collect all the eigenvalues corresponding to the eigenspaces we want to average. So I'm trying to average the second eigenspace up to the kth eigenspace. Remember, we always leave out the first one. So that is this bold set K, okay? And K bar is everything else. So K bar is lambda 1, which will be averaged by whatever we choose. So we don't care about it. We put it into K bar and we put all the other eigenvalues corresponding to eigenspaces that we don't want to average, okay? So this is the split. And this split allows you to color the square matrix consisting of eigenvectors, which we call U in that example from before. We color the different eigenspaces we want to average blue. So here I want to say average lambda 2 and lambda 3. So I'm going to color those submatrices inside the eigenvector matrix blue. And everything I don't want to average, which is in this K bar, I will color pink, okay? So please don't get confused about lambda 1. It's kind of special. We are averaging it, but we put it with the pinks. The pinks are the things we don't want to average, and the blues are the ones that we want to average, okay? So the square matrix that we had now gets these two colors, and I'm going to split the matrix apart so that the blue matrix is separated from the pink matrix. So we split the matrix, the square matrix, into two submatrices. And then we're going to pass from the rows of the matrix, which were the eigenvectors, to the columns of these colored matrices. So we switch to the columns. And this configuration of columns, I'm going to call U sub K if it comes from the parts we want to average. And we're going to call it U sub K bar if it comes from the parts we don't want to average, okay? So remember, the rows of this matrix are the eigenvectors, but we are first split them and then pass to the columns, okay? And the definition of this polytope that we care about is that you want to take the convex hull of all the pink columns, okay? So take the convex hull of all the pink columns. So this is UK bar. It's some configuration of vectors. It's ordered. Some of them are duplicates, but you have to respect them. You cannot just get rid of them. So we keep them and we remember that there are duplicates. Any case, we take the convex hull. This is called PK bar. Okay. Now PK bar happens to be a generalization of something called an eigenpolytope. So eigenpolytopes were defined by Chris Godzel in 1978 in his thesis, actually, in Australia. And there are many, many nice papers on eigenpolytopes that are written by graph theorists. They care about somewhat different questions, and the results are different from what I will present here. But this in the eigenpolytope literature, what they do is they take one eigenspace as this pink region, and then they work with that. Here, I'm allowing different eigenspaces to be stacked, but I will still call them eigenpolytopes. It's a very small difference, okay? So this is what we want to do. So the blue ones we want to average, the pink ones we don't want to average, take the columns of the pink, convexify, that is the polytope. So that's PK bar. Okay, so now let's see an example of how this works. So back to the icosahedral graph and the ordering that I had. So I want to average the first three eigenspaces, but I'm going to color the second and the third one blue, and the first and the last are pink. So the lambda 2, I don't want to average. So that one is definitely pink, but lambda 1 is added as well. And so here's the pink region, okay? So this is the pink part. And now there are 12 columns here. I would like to convexify all 12 of these pink columns. And I will get a three-dimensional polytope because the top vector is just 1, 1, 1, 1, 1. So that doesn't do anything. I will get a three-dimensional polytope. This is a full rank matrix, this part of the, because these are all basis vectors, there's no drop in dimension. So I get a three-dimensional polytope. And by a miracle, it's again an icosahedron. Okay, this is really a miracle. Doesn't always happen. And the graph theorists understand why this happens. It just happens in this example. So the polytope for us, which is this P3 bar, is again an icosahedron. And our theorem says that the facets of this polytope correspond to the minimal three designs, positively weighted three designs. So in this polytope, every facet is a triangle. So it has 3 vertices on it. So that means the 12 minus 3, 9 vertices that are indexed by the complementary set of indices form a positively weighted 3 design. So these are the minimal 3 designs in this example. Okay. So here, this picture on the left is both the eigenpolytope and the graph. And that's really, as I said, a coincidence. It's not, there's a reason for it, but it's a coincidence. Okay, so let's do another one. So here is a different ordering of the same icosahedral graph. So now I have put it in frequency order. So I want to average lambda 2 and lambda 3. So that's this blue region in the U matrix. The pink region is what you see here. So now if you convexify the columns of the pink part, which is basically convexifying this bottom bit because the 1, 1, 1 doesn't matter, then you will get a 5-dimensional polytope because this has 5 rows here, but you expect 12 vertices. But that doesn't happen because if you look closely at this pink matrix, you see that all the columns are doubled. So this column appears twice, this column appears twice, and so on. Okay, so there are actually only 6 vertices and it's 5-dimensional. So it happens to be a 5 simplex. And every vertex actually accounts for 2 of these columns. So each facet of the 5 simplex is, of course, a simplex, 4 simplex, and it has 5 vertices, but each vertex is doubled. So it actually has 10 elements on a facet. So the design is given by 12 minus 10, which is 2. Okay, so the design, the positively weighted designs in this example are just 2 elements on the icosahedral graph, 2 vertices of the icosahedral graph. Okay, so this is a first example you see where the polytope is actually less complicated than you expect. You expect some 12 vertex, 5-dimensional polytope, but you actually got a 5 simplex. And this happens sometimes. And let me show you an even more dramatic example where this happens, where the polytope is much nicer than expected. So here's another graph, truncated tetrahedral graph. And let's say we're looking for an extremal design, which means I want to average everything except the last eigenspace. So the pink part is just the last eigenspace along with these ones. And if you look at this quickly, you see immediately that what you expect is some polygon, right? It has 12 vertices, but it's a polygon. But it's actually even much nicer than that, because if you just take the pink part and look at it again, you see that every column appears 4 times. So there are 4 copies of 1, 1, 0, all these pink ones. There are 4 copies of 1, minus 1, minus 1, and so on. So in the end, when you convexify these columns, all you get is a triangle. So it's a much, much smaller polytope than you expect. And the indices of the columns you put on the vertices that correspond to them. And now, for example, if I take this facet, this red facet that you see here, the design that corresponds to it is given by the complementary set of indices. So it's 2, 5, 8, 10, and 2, 5, 8, 10 on the graph gives you this design. So this is an example of an extremal design in this truncated tetrahedral graph where the polytope is just a triangle, even though you expect something with many, many more vertices. Okay, so that's another example. Let me do just one more example because everyone likes the Peterson graph. So here's the Peterson graph. It has only 3 eigenspaces, the trivial one, and then another one with the multiplicity 4. This eigenvalue has multiplicity 4, and another one which is here. And again, here, if you want an extremal design, then we only take the eigenspace corresponding to this last eigenvalue. So that has it has 5 rows along with the 1, 1, 1, 1, 1. Now, if you take the convex hull of the columns, you will get a 5-dimensional polytope as we expect, but this doesn't collapse like the previous examples. It has face vector given here. So it has 10 vertices and 22 facets. And then these are all the in-between faces. But there's still quite a bit of symmetry. So these 22 facets come in 2 symmetry classes. There are 12 simplicial ones and 10 facets with 6 vertices. So if you're simplicial, then those facets give you designs that look like the ones you see on the left. They're combinatorial. And if you are not simplicial, if your facet is not simplicial, then you actually get a smaller design because 10 minus 6 is only 4, but these are no longer combinatorial. You actually need to assign non-uniform weights, but they're still positive. Okay, so these are all the examples that I wanted to show you that shows you the construction in action. Okay, so the motto we want to have here is that there are many graphs for which these polytopes turn out to be very nice. They're not always nice. They can actually be quite wild, but in many examples, they are nice, and you can read off information about the positively weighted designs from these polytopes. Okay, so those are basically the examples, and now perhaps I can spend 5 minutes just explaining why it works. So the reason this whole construction works, again, if you are an expert, you probably already realized this. It's because of oriented matroid duality. Okay, so I'll be very brief about what I mean by this. So if you have 2 configurations of vectors, so let's say we have blue vectors and we have pink vectors that are written in this way, like in this cartoon. The first set of vectors I will call U, and the second set of vectors, let's call them U star. And now if the pink matrix and the blue matrix multiply to give you 0, then we call these 2 configurations dual configurations. Okay, so these are 2 dual vector configurations. The matrices have full rank in both cases. And so this is exactly the situation that we have. We have a blue set and a pink set, and the product is 0 because of orthogonality of the eigenvectors, right? Because the eigenvectors are rows of the blue and the columns of the pink. So they are orthogonal to each other. So we get dual configurations. And whenever you have 2 dual configurations, then there is a polytope and a vector configuration that share information or have the same information. So let's start with the polytope side. So let's say I have a pink configuration and a blue configuration. So the pink one, I have 1, 1, 1, 1 on the top. And so if I take the convex hull of that, I will get a polytope. So in this example, I get an octahedron if you convexify these 6 columns that you see here. There is no doubling, so you actually get an octahedron. And now the key result is that if you look for a facet, more generally a face, but let's just say facet of the pink polytope. So let's say a facet, this facet that's given by 1, 3, and 5. So it's the convex hull of the vector 1, 3, and 5. Then it corresponds on the other side to the blue vectors that are given by the complementary set of indices. So 1, 3, and 5 on the pink side means I need to take 2, 4, and 6 on the blue side. And they will have the property, the blue vectors that you pick will have the property that 0 is in the relative interior of that convex hull. So anytime you have a facet, or in oriented matroid language, a positive co-circuit, then on the other side, you will have the complementary set of vectors will contain 0 in its interior, in the interior of its convex hull. Okay, so this is Gale duality. So this allows you to read off facets or faces of the polytope from the structure or the positive circuits of the dual configuration, which is the blue configuration. So that's basically what's happening in these examples. So here is again Gale duality written out precisely. So as I said, every facet on the pink side corresponds to the complementary set of blue vectors having 0 in its relative interior. And here's a non-example. So for example, 1, 3, 2, 4 does not form a facet. So the complementary set is 5 and 6. So if you look at the vectors 5 and 6 and take their convex hull, it does not contain 0 in its relative interior. So this is the Gale duality theorem. And so written formally, it says if you pick an index set I from the set 1 through n, and if you convexify the vectors in U star given by n minus I, then this is a face of the convex hull of the U star configuration, if and only if 0 is in the relative interior of the convex hull of the blue vectors that are indexed by I. Okay, so this is a bit technical. It doesn't matter if it's not fully clear, but hopefully the picture is clear. So the reason it works for us is because when we're looking for designs, we're looking for these weighted averages that give you 0. So that's exactly the same as working on the blue side. We need to find positively weighted combinations that add up to 0 on the blue side. Instead, we pass to the pink side and look at polytopes, and the faces of that polytope tell you the designs. This is exactly the structure that comes out. And everything works beautifully because of the orthogonality of the eigenvectors. So the configuration and its dual configuration are both sitting inside the matrix of eigenvectors. So it's very, very convenient and very fits very perfectly. So that's that. So the consequences of this are, as I said, first of all, there's a polyhedral structure behind the set of all K designs. So you give me a graph, you give me an ordering of the eigenspaces, and you give me a K, then I can produce for you this polytope, which, sorry, it turned blue, but the polytope is pink. And the facets and the faces of this polytope index the K designs of the graph. The facets give you the minimal ones, and the faces give you less and less minimal ones. Okay. So that's one structure, which immediately means that there's also an adjacency structure on all these positively weighted K designs. So here's the Peterson again. So this is like a zoomed in picture at one design. So this is a combinatorial design on the Peterson, we saw it. And it is adjacent to all these other ones, which are all isomorphic, that are positively weighted designs, but they're not combinatorial. So this is just one design and its neighbors, and you can extend this graph to get an entire graph of K designs with all the edges and the higher dimensional, with all the edges basically indexing non-minimal things. So there's a really nice polyhedral structure on these K designs. Okay, so that's the main theorem. And one of the consequences of this theorem is that it shows you that for every value of K from 1 to m minus 1, there is a positively weighted K design whose size is at most the sum of the dimensions of the eigenspaces that you want to average. Okay. The reason is very, very simple, because we just saw that if you're looking for a K design, then corresponding to it, there's a polytope. The polytope has a certain dimension, which means its facet has a certain dimension, which means the facet is at least a simplex, which means it has at least so many vertices, which means the design has at most so many vertices. Okay, so you immediately get an upper bound on the size of the designs from this polyhedral construction. And this was apparently not very obvious to the analysts. And using this, you can connect. So once you have this existence theorem for positively weighted designs for every value of K, then it turns out that you can connect this to random walks and all kinds of other combinatorial objects. And I will mention a reference at the end that does this. So this is a simple consequence of this polyhedral theorem. So there's an upper bound on the size of positively weighted designs, and they exist for every value of K. Combinatorial designs don't exist for every value of K, but positively weighted ones do. And the lower bounds are just trivial. So there are examples where there's only one point sometimes that's required, one vertex. But the upper bound is given by this, and the upper bound is tight. So there are examples of graphs where this bound is reached for every value of K in the same graph. Okay, so that's basically the main part of the talk that I wanted to explain. And once we had this theorem, we were able to actually work out several families of graphs and the sizes of their designs and optimize them and so on. In the paper we worked on 3 families of Cayley graphs, cycles, cocktail party graphs, which are these the edge graphs of cross polytopes, Those are both fairly simple. There's a bit of number theory in the cycle part. The cross-polytope part is pretty easy. And the hardest family we tried to work on was the graphs of hypercubes. So this is, of course, relevant in many, many disciplines. Computer science especially has thought a lot about graphs of hypercubes or Boolean hypercubes. So I will just very briefly tell you what happens in this case. We don't have a fully complete result, but we made some progress. So if you let QD be the edge graph of the 0, 1 cube, then the eigenvalues and the eigenvectors are known. Okay, so the eigenvectors, they are the characters of the group Z2 to the D, so they are known. There are, of course, many, many different eigenbases, but this is one. They're very nice. And once you know the eigenvectors, you know the eigenvalues. So that's the advantage of working with Cayley graphs. You know the eigenvectors. In general, lots of people have worked out eigenvalues of graphs, but not so much is known about eigenvectors. So this is an example where they are known. And in this case, if we let Pi index the eigenpolytope of lambda I, then P0 is, first of all, I should say the eigenvalues are given by this formula, 1 minus 2i divided by d, and I goes from 0 to d, okay? So that's how you index the eigenvalues. And the interesting eigenpolytopes are the ones beyond P0 and PD, okay? So it turns out that if I is odd, then the polytope is centrally symmetric and has 2 to the d vertices. And if I is even, then there is a doubling of the columns and the polytope is more complicated and has 2 to the d minus 1 vertices. Okay, so I will go fairly fast through these because I'm not hoping to really have you, I'm not expecting that everything can be absorbed quickly. There's a lot of indices, but I just want to give you a sense of the type of results. So if we're looking for extremal designs, then it turns out that if the m that corresponds to the last eigenvalue is roughly given by these formulas. So depending on the congruence class of D mod 4, you get different indices for the ones that we want to leave out. Okay, so there's some little bit of number theory showing up. And when D is 2 mod 4, we have a completely final answer, in the sense that if D is 2 mod 4, then the minimal extremal designs are all combinatorial. In the cube, they are always, we expect, because of the high amount of symmetry, we expect combinatorial designs to exist for all values of K. And these, in this case, we know exactly what they are. They consist of 2 to the d minus 1 vertices, and we can also say what they are. But the surprising thing with these hypercubes is that we did not get these results by using our theorem. So we got these results by actually working with codes. So these designs are actually linear codes. And it's actually hard to work with the theorem that we proposed. In fact, you can get information about the polytopes from these codes. So this example is a code. It's a linear code. And a code just means the kernel of a 0, 1 matrix living inside the vector space 0, 1 to the d. Okay, so a linear code C is the kernel of a matrix inside the vector space 0, 1 to the d. And Catherine had, in an earlier paper, proved some results about codes. And then using that theorem, we can write down a bound on the size of extremal designs. So here's our theorem. It says that QD, which is the graph of the D hypercube, this has a positively weighted extremal design of size at most 2 to the d minus t, where t is pretty big. So again, lots of formulas, but the point is that you can write down some codes and, you can write down some bounds. And these results are also found through coding theory. So it turns out that there's a way to generalize Hamming codes. There's a theorem by a person called Bonisoli, and Bonisoli has a theorem about how you can stack Hamming codes together to get what are called equidistant codes, I believe. They have some technical name, which I can't recall right now. But using that construction with codes, we can give a bound on these designs. So let me just finish by showing you roughly what happens. So in this case, as I said, if D is 2 mod 4, we have an exact result. So 2 and 6 and so on The best extremal designs you can get will have size 2 and 32, etc. But for all the other congruence classes, we only have a bound. So let me just focus on one example, like this line that says 7 here, d equals 7. This is the 7 cube. The eigenspace we want to not average is the 4th eigenspace in frequency order. The polytope we get will have dimension 35. It's a binomial coefficient. The polytope from our theorem has 64 times 2 vertices. It's supposed to have 2 to the 7 vertices, 128, but there's a doubling, so it has 64 vertices. And the design we can find has size 16. So this design is the Hamming code. It's the Hamming code on the 7 cube. Hamming codes don't exist in all cubes, but in this case, it is the Hamming code. All the other things that we construct here are basically extensions of the Hamming code. So this is not optimal. We don't know that they're optimal. Actually, we don't know that they're optimal. So we conjecture these designs are optimal. They're very, very small designs. So for example, 16 vertices are enough to average all eigenspaces of the 7-dimensional cube graph, except the last one, okay? And on the polytope side, it gives you some information about the polytope, but the polytope is not the thing that gave us these answers. Okay, so let me finish by just showing you one more example. So here is a real-world example of a graphical design. This is a graph on 2,277 vertices, which correspond to Wikipedia pages that are related to chameleons, okay? And the 2 vertices are connected together if they have a hyperlink between them. And in this example, what the red vertices you see here, this is not a regular graph, but what you see here is 228 red vertices that form a 229 graphical design. So this is about 1/10 of the vertices, and they can catch 229 of the eigenspaces. Sorry, I don't remember how many eigenspaces there are. There's probably a lot of eigenspaces. As you lose symmetry in the graph, the eigenspaces become closer to one-dimensional spaces. So this is a picture from an article that'll appear in the AMS notices written by Catherine, one of these "What is" article. And so we did an example like this, or she did an example like this. So that's an example, and here are some references. The main paper is the first one. It's going to appear in Math Programming. Stefan and I have another paper that connects designs to random walks, if you're interested in that, and also to graph sampling. And if you want to see lots and lots of pictures, there's a whole gallery that Catherine maintains on her webpage, where you can see many, many pictures of graphical designs. And if you'd like to contribute to them, please send her an email, compute one, she'll put it on the webpage. Great, thank you.
Thank you, Rekha, for this wonderful talk. Do we have questions?
Hi, thank you for the talk. I was just wondering if this was related to design theory at all, or whether it was just a naming coincidence.
Yeah, this was very confusing to us in the beginning, because we were so worried that this is something that people know. It turns out that it's not exactly the same thing. So the closest this gets to are things like T designs and association schemes, then they are roughly the same objects. So Catherine has a paper earlier on. I think there are many things called design, so I'm not exactly sure how to answer the question, but it appears to be a new concept that is actually not known. So Catherine's first paper is a paper that distinguishes these graphical designs from other notions of designs and stable sets and all sorts of things that could possibly be the same thing. So we wondered whether, are these just stable sets, or are these, some sort of, other known object? But so far it seems they are not known. This is truly a new object that was motivated by these analytic sort of considerations, and it appears to be new. And but I'm sure there are situations in which they will coincide with some sort of design that you might have thought about.
Thank you.
So have you tried looking for some statistics on designs in FindStat? Because they have graphs in that database, you can search and see if it's related to something that's already known.
You mean some sort of statistics on the designs?
Yeah, I mean, so if you have a given graph, you can see what's the maximal K where you have a K design.
Okay.
So that's a
So
statistic.
by our theorem, yeah. So by our theorem, for every K, there is a positively weighted design. Combinatorial ones, no. So it would be so we don't know a lot about this. As I said, it's a fairly new area. So the Stefan's papers from 2016 appeared in 2020. There seems to be a total of 4 papers in this area. So I think there's a lot of things to do, and it connects to many, many areas of mathematics, probability and, analysis. So how do you, as you increase the size of the graph, so you can do some sort of extremal combinatorics with it. It's related to representation theory. There's a lot of symmetry in many graphs. So I think the number of questions is sort of very, very large. So what we know is some of the best things we know are what I presented. There are some more things that are not written, but not a lot is known. Yeah.
Okay, so then you should submit this to this FindStat database so that other people can connect it to other areas if it's not there.
Yeah.
Thanks.
So thank you.
Sorry? No, but you can, there's a statistic, right? You can see the largest K such that you have a K design. That's a nice statistic. Okay, thanks.
For combinatorial designs. Yeah. For if you don't want combinatorial, there are designs for every K.
Okay, thanks again.